I'm Ken Armstrong, President and CEO of North Arrow Minerals, and the following is a recent conversation I had with Bruce Johnson discussing the Remote Mapper UAV survey system. Bruce is a lead member of the team at Mineral Services Group responsible for the development of this magnetic survey platform. Remote Mapper collects high-resolution and impressively quiet magnetic data very quickly and cost-effectively, and it's a key tool being used to see beneath the Kalahari sands that cover North Arrow's Kraaipan Gold Project in Botswana. Bruce is an electrical engineer by training, and he's been developing and optimizing Remote Mapper for over the last 12 years. Remote Mapper has been successfully used across the globe, rapidly producing high-resolution magnetic data in many different terrains and environments, including in northern Canada and Botswana. We really believe that Remote Mapper is a game changer with respect to the rapid and cost-effective collection of magnetic data for exploration projects, and I hope that you find my conversation with Bruce informative. I'm Ken Armstrong. I'm the President and CEO of North Arrow Minerals. And one of the key pieces of technology we've talked about using for the exploration of our Kraaipan project in southern Botswana is the Remote Mapper survey unit, which we see right in front of us. And I'm with Bruce Johnson, who's one of the key members of the team with Mineral Services that's developed this unit, and he can answer a few questions that I think that we've all had about why this unit is such a game changer when it comes to collection of magnetic data.
Perfect. Thank you, Ken. So as Ken mentioned, I'm Bruce. I'm an electrical engineer, and we've been developing this system for the past 12 years. It is currently operational, and it's formed part of a suite of tools that have allowed us to capture magnetic survey data, so aeromagnetic data, cost effectively and rapidly over large areas of land. What makes the system different is that we fly at approximately 90 kilometers an hour, and we have an endurance of approximately 3.5 hours. So we can cover a significant amount of land over that period, that flight period, and that allows us to capture magnetic data cost effectively and rapidly. The fundamental difference between this aircraft and other aircraft that may have been used for magnetic surveys is that this aircraft has been designed specifically for the purpose of capturing magnetic data. So the aircraft has some unusual design characteristics, but that's all driven by the payload requirement. So if I show you the aircraft, this aircraft is powered by a conventional two-stroke petrol engine and carries a potassium magnetometer in its tail over here, and everything is designed to be magnetically quiet. The system has always been intended to be used so as to create or produce magnetic data that's exceptionally clean, so that very, very little post-processing is required to create the actual data product that's used for interpretation. Some other key points on the aircraft are that the whole system is designed to be modular. So if, for example, a component needs to be replaced for whatever reason, it can be unplugged and a new one placed in its place. So, for example, the tails can be replaced, fuselages are in two pieces, the engine is a module, and the autopilot is a system that we've built internally within our company, and it's designed to be a modular system that can be removed rapidly and replaced in field by very quickly. In addition to that, it provides a lot of safety systems on board, and it does the interface to the magnetometer. The autopilot includes a companion computer which serves as a payload management tool. It allows us to monitor the aircraft both in terms of the actual flight control system, so to manage where it's going and the height that it's flying at, and the various safety systems that are associated with it. But in addition to that, we can monitor what the payload is doing to make sure that we're not experiencing any issues, and that if we do experience an issue, we can bring it back home and deal with that. The engine on the aircraft is a conventional two-stroke engine, as I mentioned. It's been adapted for the use of a UAV, and it's a completely modular system. So the whole thing can be unbolted and replaced as necessary. And then, in addition to that, the aircraft is designed to be very robust. It's simple in its construction, which means it's a lot simpler to maintain, and it's designed exclusively for harsh terrain. So while other aircraft may be a little bit more polished and look a bit more attractive, it's designed to be simple, robust, and effective in its job.
So, Bruce, you talk about it collecting high quality, really quiet data. So what is it about this unit that makes the data so quiet and not requiring so much processing?
The key factors that allow us to produce that kind of data are that the aircraft, as I mentioned, is designed specifically for magnetic surveys. So the construction techniques used within the aircraft minimize the use of any ferrous or metallic or conductive materials, so as to reduce any attitude-induced effects on the magnetic signal. In addition to that, we're able to fly low. We typically fly at 30 meters above ground, and we load a terrain database onto the autopilot in advance, which allows us to drape the terrain so that we can maintain a constant terrain separation envelope throughout the flight. In addition to that, we are obviously using an autopilot, which allows us to fly very accurate lines, typically with a cross-track error of less than 1.5 meters. So we're able to capture accurate positional information for where we capture the magnetic data, the sample point. In addition to that, we're able to fly accurately. So we can cover the large tracts of land accurately and repeatedly.
Great. So Bruce, like a 3-hour range is huge, right? For this thing to get up in the air and it can fly continuously then?
Correct, yes.
For a survey. And so how does that transition happen from takeoff to the autopilot and the grid that you've already programmed in for it to fly and then landing? How does that all work?
So before a flight has begun, the autopilot is loaded with a waypoint file, which will be decided upon based on the survey polygon that you want to cover. Once the waypoints are loaded, the engine is started and the aircraft is warmed up, and then an operator will take the aircraft off a runway. We typically need around about 100 to 120 meters, depending on the surface, and then climb out to around about 80 meters is a safe height. Once at altitude, the aircraft is commanded into automatic flight mode, and it will then proceed to its first waypoint to cover the intended survey area.
So Bruce, like productivity is one of the key things about this. It's high quality data, can be collected quickly. Like what would be a typical or a maximum amount of coverage that you get in a day of flying with the unit?
So in the areas that we operate, a good day would be around about 1,000 line kilometers per aircraft, and we typically aim to fly 2 aircraft at a time, so we can cover a significant area during that day. And
that's huge, right? Because that's sort of, you have a crew out, you have 2 aircraft, you're collecting up to 2,000 kilometers of data in a day versus walking mag, which would be the equivalent that we're trying to replicate with the system,
right,
which would take far longer when a person can walk maybe 20 kilometers in a day and
correct,
yes, data. Like that's just to give an idea of how much more productivity we can get out of this unit.
That's correct. And the typical operation would consist of 2 to 3 vehicles carrying the aircraft, some of the support equipment, and then obviously the field equipment that the guys would use when they're camping.
And so a 3-hour range, and it's 2 liters of petrol? Is it,
we carry approximately 6 liters of petrol,
okay.
And we leave a healthy margin of fuel so that we ensure that we have a healthy safety margin.
So Bruce, we talk about like a 3-hour flight time, but how big a grid could be covered from obviously where it takes off and it needs to come back and land there? So what sort of distances away from that central area are we talking?
So we have a telemetry system on board, which you can see over here. These are the 2 aerials, and that allows us to communicate with the aircraft in flight. It allows us to get information back from the aircraft to see the speed and the height and various other safety metrics. But in addition, it allows us to control the aircraft. So the telemetry system allows us to run well in excess of what our regulatory limits are. In South Africa, we're approved to a 10-kilometer beyond visual line of sight approval. And in other jurisdictions, it varies, but we typically target around about 10 kilometers from the takeoff location. So what that means is that you can fly, if you have a well-placed takeoff location, you can fly, for example, 10 k's north and 10 kilometers south. So your
maximum line length of about 20?
Yes,
probably slightly.
around about, yes. So your lines are long, which means you can have long, consistent lines. And if, for example, there is a telemetry dropout zone, for example, because of terrain, we are able to place repeating telemetry stations at strategic locations in order to fill in those gaps. As part of our initial site survey, we identify these areas and we'll place repeaters and then do a test flight to make sure that we have full coverage over the intended flight area.
This has been in design for 14 years or so, but you've been flying surveys for quite a number of years in different areas. I know in Canada, in the diamond, up at Acadie, for instance, up
Yes.
the diamond mine there. Where else has the unit been flown?
So we've flown, in addition to the Canadian Arctic, we've flown in northern Sweden in the snow. We've flown in South Africa, which is where we are currently. And we've flown significant surveys in Botswana, which is to date been our largest location.
Yeah, which is perfect, because that's obviously where the Kraaipan project is, and we're utilizing some of those existing surveys, and then going to be very shortly, if not in the next month or so, flying additional surveys to cover the rest of the belt. Bruce, this unit is really unique. Eh? There's nothing else like it on the market, either for commercial use or otherwise. It produces data quickly, and it produces it cheaply with a long flight range. Very quiet data that requires minimal or no processing. It's been used in a number of different environments and terrains, including in Botswana and northern Canada, which is an area that I know well. One of the things we do see, of course, is it's on wheels, so that requires a runway to take off.
Correct.
Is there sort of a next step for this to maybe not have to rely on a runway?
Yes. So we've got a development program underway to produce a vertical takeoff system for the aircraft. That would be a vertical takeoff and then transition into level flight system. The system is still under development and will require a fair amount of work to get into production. But the goal of it is to reduce the operator skill requirement so that a person can program the aircraft and it can take off and land by itself with no runways required. And then in addition to that, provide an additional safety assurance that if, for example, there is an engine failure or some other kind of failure on the aircraft, we can detect that and then we can initiate an emergency landing. So in addition to the operator skill requirement, it brings the safety case of the system up.
And just the logistics of not requiring a strip on which the aircraft needs to
That's
land
correct,
or take off on. It will be a far broader range of areas that you can then operate in.
Yeah, to date we've typically selected pans or roads or other flat areas in which to operate, so that we can get a space of ground that we can take off and land from.
Why this is so important for Kraaipan is it's going to allow us, with our partner Rockman, to collect really high quality magnetic data beneath the sand that will allow us to see what's happening in the geology beneath the sand cover in the property area. And we'll be going through in the first stage of exploration with some structural mapping of the areas of outcrop that we have for these iron formation deposits, hosted deposits that we're looking for. But having the remote mapper data to then translate what we're seeing in the rocks to what we see in the magnetic data, we'll then be able to extrapolate that magnetic data beneath the sand cover, and it's going to be a really important piece of our targeting areas of potential mineralization as we move forward and advance the exploration on the property.